In our last two examples, we want to find the derivative of a given function. We want to evaluate that function for a specific value, evaluate that derivative function for a specific value of x. And then in the last example, we'll also add on again finding the equation of the tangent line at that point. So using this four-step process, again, the first thing that we want to find is f of x plus h. So that means anywhere we have an x in our function, we'll plug in this expression x plus h. Our function in this case is 2, so there is no variable to substitute anything for. So f of x plus h is still just 2. Step 2, we want to find f of x plus h minus f of x. So f of x plus h is 2, minus f of x is also 2, which gives us a value of 0. So then we want to find f of x plus h minus f of x divided by h. So that numerator we know is 0 divided by h, which gives us a value of 0. And then in the fourth step, we want to evaluate the limit as h approaches 0 of this expression. So in this case of 0, the limit of a constant is always just that constant. So our result here is 0. So what this means is that f prime of x, so the derivative of the function 2, is 0. And it would also tell us that f prime of 1, meaning we'll substitute 1 into our derivative function, is still also going to be 0. So the rate of change of our function at x equals 1 is 0. And in this case, in fact, since we have a constant, the rate of change of our function is always 0. So if we look at the graph for this function, that should be fairly intuitive. We're considering the graph of y equals 2, which is a straight horizontal line, never increasing, never decreasing. So it has a slope of 0. Since the derivative function tells us about the rate of change of that function, it makes sense then that if our slope is 0, our rate of change should be 0, and at any value we plug in for x, we're still going to get that rate of change to be 0. So anytime we take the derivative of a constant, that result will always be 0. So that was sort of an easier case to consider. Example 6 is going to be a little harder because now we do have something to substitute. We'll again follow that same four-step process. So the first thing we want to find is f of x plus h. So our function is 1 plus 3 times, and now in place of that x, we'll substitute in x plus h, that quantity squared. So we can go ahead and expand x plus h to give us 1 plus 3 times x squared plus 2xh plus h squared. And then distributing the 3 through, we'll get 1 plus 3x squared plus 6xh plus 3h squared. In step 2, then, we want to find f of x plus h minus f of x. So our expression for f of x plus h and then we want to subtract the original function, 1 plus 3x squared. So I put this second function, f of x, in parentheses just so that I know that derivative should be distributed through. So really we could come back and rewrite this as plus negative 1 minus 3x squared, which means our minus 3x squared and plus 3x squared will cancel, minus 1 and plus 1 will cancel, leaving us with 6xh plus 3h squared. So then we want to find in step 3 f of x plus h minus f of x divided by h. So taking this result that we already have and dividing it by h. So since we have an h that's common in the numerator, we can factor that out to rewrite this as h times the quantity 6x plus 3h all over h, which means the h's will cancel, leaving us with 6x plus 3h. And again, this is going to be the key to evaluating these derivatives because we need to evaluate the limit of this function as h approaches 0. So the real goal is going to be to get that h in the denominator to cancel out, which means we'll be able to evaluate the limit as h approaches 0 of 6x plus 3h using direct substitution. So we get a result of 6x, meaning that f prime, the derivative of our function f of x, is equal to 6x. So now what we have is a function, the derivative function, that gives us the rate of change of our function for any value of x. So if specifically we want to find f prime, or actually I guess in this problem I called it r, so let me change that here. So in this problem we actually started off with r prime, and instead of this being f of x, this probably should have been r of x. That would make a little more sense. Sorry for the typo there. So r prime of x is 6x. If we evaluate r prime of 2, what we're saying is what is the rate of change of our function at exactly x equals 2. So we just make that substitution into our derivative function to get that the rate of change is 12. So if we know the rate of change of our function, that's the same thing as the slope of our tangent line. So to get the equation for our tangent line, we can set up an equation of the form y equals mx plus b, where here our slope is going to be 12. And now we need to make substitutions for x and y. We want the equation of the line tangent to our function at x equals 2. So for x, we'll substitute 2. And for y, we'll substitute f of 2, which will be 13. So this gives us 13 equals 24 plus b. Subtracting the 24 from both sides then gives us negative 11 equals b. So we know that the equation for our tangent line will be y equals 12x minus 13. So we have, in this case, again, a few different results we found. We found the derivative of our original function, which lets us know the rate of change for our function at any value of x. We evaluated r prime of 2, which gives us the rate of change, or again, the slope of our function at exactly x equals 2, which was 12. And then we use that slope-intercept form to construct the equation for the tangent line.